Hi, this is going to be the first lecture on a series on topology, and many students have been asking for that for a very long time. Start with that. But I would like to say something about topology. Usually teachers always start with saying something like rubber sheet geometry, etc., etc. Okay, I don't want to build any such thing. You will see at the end what we really have achieved. So topology, I want to treat it as a kind of discipline. Okay, like the way Euclid's geometry started with axioms and proved theorems, and this is some kind of modern geometry. Okay, using certain axioms, and it is geometric because we are going to draw a lot of pictures to build our intuition. But then any proof will be very rigorous using only the stated axioms. Okay, so that way it's a very good training ground for mathematics. But rest assured, okay, we'll finally, whatever the vague ideas about rubber sheet geometry, this and that, all those things, continuous deformation, everything will come. Okay, but in the beginning you should not get over excited by such things. Okay, number one. Number two, I am going to assume that you have already gone through some basic ideas about metric spaces, at least up to the definition of the class of open sets. Okay, I would strongly recommend please watch the first 4 videos on metric spaces, okay, by me, which is available in YouTube channel. Okay, please do that. And if you are not done, even if you think you had already learned metric spaces, open sets, etc., please have a look at them. Okay, you will see they are different. You will get a very good geometric intuition, which will be very useful for the course. Okay, number one. Number two, this we are going to use a lot of set theory. Of course, in modern mathematics, we use a lot of set theory, especially topology. And teachers do not spend time that students have not seen an arbitrary collection of sets and their union, their intersection, complementation, De Morgan's law. Okay, except for a pair of two about a finite number of sets, you might have done all those things. But arbitrary collection may be countably infinite, uncountably infinite. You don't even know what they are. Okay, how to deal with them. And unless you are very thorough, just don't go by intuition, so I know how to deal with that. Okay, don't do that. Please try to learn that thoroughly. And for that, again, I will suggest my lectures on arbitrary unions and intersections of subsets. That's again available on YouTube. And let me repeat, please stop the video here. Okay, go back and watch them. Okay, and if you don't be in a hurry, you may think that you had already learned. Many students make that mistake. You will see there are a lot of interesting things which you may not have noticed. Okay, and the way I approach a subject, which will build your confidence and geometric intuition. Please go through the first 4 videos of metric spaces and the video on arbitrary union and intersections. Okay, that is also available in one of my foundation course lectures which I gave recently. Yeah, okay. So with this, let us get started. So today's idea is that I will introduce what is meant by topological space and try to give some examples. Okay, and the second lecture may also continue with that, because in any subject, this is my standard practice. You might have seen that I always kind of build a good set of examples. So whatever the concept throughout the course we are going to learn, I'll come back to these examples and try to see them. Okay, that is the way you become confident of abstract theory, and also at the same time you are faced with some new problem. Okay, how to solve it, then your familiarity with this standard set of examples you can go through and understand and come back. Okay, this has nothing to do with topology. Go to algebra. Okay, anything, any new subject, always do that. For example, if you go to differential geometry, again you should have a very good set of surfaces, manifolds, okay, level sets. These are the basic examples. These are standard trick. Okay, please learn them very thoroughly. Okay, right, let me get started. Okay, the references, I am writing a book on topology which is likely to come soon, let's say about within a year's time. And it is also based on a course of lectures I had given at various places. Yeah, okay, it is written as an outline of topology. You may download it from OD space. Of course, there is always the standard reference Congress, right? Okay, now what we want to do, so let us I will quickly recall. Suppose xd is a metric space. Okay, then a subset u of x, when do you say it's open? D open or simply open? Okay, this is my x and this is my u. Okay, I have a point here. Take any point. So if for every x in u, okay, there is an r positive, so that bxr is contained in u. Okay, this is open ball, right? This is the definition of open sets in a metric space. Now if I look at tau, or if tau d, okay, the collection of d open sets, I will not say hereafter d open sets. When the metric d is fixed, I will simply refuse. Okay, then what are the properties it does have? The first property is empty set and x, they belong to tau d. Okay, tau. And second thing is, if this is what I said, if u is an arbitrary collection of tau d, if you want you can write as, it may or may not be possible ui where I is an indexing set, then the union ui I in I also write it as union script u. So my video on arbitrary collection, arbitrary union or arbitrary collection and intersections will talk about these things. Please learn that this again belong to tau d. And the third thing is easy. If u and v are open, then u intersection v is open. Okay, these are very easy to prove. I'll just indicate a proof for 3 because this is very easy. Because if suppose I have this each ui, I want to prove, let us prove 2. Okay, let x belong to union ui. What do I have to prove? I have to find an r. Now x belong to union ei implies there is an I in I, that x belong to ui. That means since ui is open, that means there is an r positive, that bx r is contained in ui, and therefore it's contained in union ui, right? Therefore, given any x in union ui, I have proved there is an open ball which is contained in the union. Therefore, this implies union ui belong to tau, right? Now 3 is more interesting. I want you to pay attention. Suppose u and v are open, and if u intersection v is empty, there is nothing to prove. Okay, so let's assume this is not empty. Let u intersection v belong to this. What am I supposed to show? I have to show there is an r positive, so that vxr belong to u intersection v, right? Okay, so does it happen? Now there is an r1, so that bx r1 belong to u, contained in u, and bx r2 contained in v, right? So again, let's look at a picture. The picture may be like something like this. So I have u, okay, and this is my x, okay, maybe sorry, this is my x, sorry, this is my x, okay, and these are two open set, okay. This is a open set u, this is u, and there is another open set v, this v, okay. Then what do I do? Okay, there is an open ball here, which means here. Okay, this the same notation which is contained in this. There is an open ball which is contained in, right? But x has to be common, right? So the picture is not good. So how should I draw the picture? This is my x. This color is not good. Let me choose different color. So this is my x. Then this is bxr and r1, and there may be another bxr2. Either this may be bxr2 or this may be bxr2, right? With the same as the center. Okay, the picture is wrong. Let's not worry about. Therefore, what do I do? Let r equal to minimum of r1 and r2. Then bxr is contained in bxri r1, and hence is contained in u, and this is contained in bxr2, and hence is contained in v. Therefore, bxr is contained in u intersection v. Do you follow that? Yeah. So that's how we proved intersection of two open sets again open. But I want you to pay attention to the proof. How did we see that? What we had was, let's not worry about R1 and R2. Let's look at, call it as B1 as BR1 and B2 as BXR2. Then what I know is X belongs to BR1, which is contained in U, and X belongs to B2, which is contained in V. Then I looked at B1 intersection B2. If I know there is another open ball B, so that X belongs to B, okay, and B is contained in B1 intersection B2, then I have proved the result. Yeah, pause, review. So like all modern mathematics, what we do, we appropriate these three properties. Okay, we abstract these properties. Suppose I am given a set X, okay, assume as usual non-empty, okay, and suppose I have a collection tau which is P of X. This P of X is the power set, that is, okay, class of all subsets, a set of subsets of X. Okay, right. So what I want is tau should have three properties. What are the three properties? We simply mimic the earlier one. The empty set and X should be in tau, and 2, if U is an arbitrary collection in tau, then union U should again be tau. That is, I have arbitrary collection of open sets, sorry, arbitrary collection of subsets in tau, then that union also be in tau. Okay, and the third property is, if I know U and B are in tau, then U intersection B also is in tau. Right? If you want to write script U as a collection UI, then this is union U is same as union of all UI I and I. This must be again in tau. Is that clear? Right. Now we are going to declare, okay, there is nothing like open anything. Now we are going to declare any member, that is, it's any subset, right? Any subset in E, tau is called an open set in the topology tau. In the topology tau. Tau is called the topology. Okay. So any collection tau satisfying these properties will be called a topology, and any member in tau, that's a subset of, okay, if I have a subset U, suppose I have a subset A of X, and if A belongs to script U, then I am going to call A is open. Sometimes I will say A is tau open if there seem to be two topologies on that. Is that clear to you? Now notice that now there is no intuition at present, right? The open etc. in the metric space, we have some kind of intuition. When I wanted to say it's open, what did I find? Given any set U and any X inside, I should be able to find an open ball which is completely contained in U. Okay, there's some kind of intuition over there. Here there is nothing. You only have a collection of subsets satisfying these three properties. That's what I said. It's something like Euclid's axiom and doing Euclidean geometry. Unfortunately, modern, young people like you may not have done that, but when we were students, we learned about 100 theorems. That gave us a very, very good way of logical thinking. And this is going to teach you, don't worry. Okay, we are going to teach you this. Is that clear to you? Yeah? Okay. Right. So the pair x tau is called a topological space. Okay, and tau is a topology on U. Okay, and any member A, if A is in tau, then A is tau open. We may not say tau unless there is some confusion. Is that clear? Okay. Now let's look at simplest example. Of course, the first example is a metric space. Suppose XD is a metric space. Okay. Now what is tau? Now tau is what we started with. It's a collection of open sets. And what we saw, this tau satisfies the three conditions. In fact, our conditions on topology, we are inspired by this, right? Yeah. So this is a collection of open sets. This is a topology. So this is called metric topology. Metric topology on X. Sometime I will call it D. Okay. Metric topology or D topology. This is the first example. Are you sure about this? As a simple corollary, you should immediately special cases. We should always keep special case in mind. When x equal to r, our standard metric dxy equal to mod xy. And you know what are all the open balls? Open balls are open intervals, right? All of you should know that. If you have watched my videos, you should know these things. And similarly, I can take x equal to rn, right? And there the distances, any one of the metric. D may be d1 or d2 or d infinity or d max. Okay, I'm not going to explain these things. As I said, I warned you already. You have to go and watch them. Okay? Yeah, I'm not going to repeat. Very good. Okay. The second thing is the simplest thing. Suppose I have x is a set, and let's look at px. Does px satisfy all the three properties? What are the three properties? Empty set should be there, the full set should be there. You take any collection of subsets and its union should be again in that collection tau. Of course, right? You take arbitrary collection of subsets of x, take their union, it's again a subset of x, and therefore it is going to be in the power set. You follow that? And similarly, u intersection b is a subset of x, therefore it again belong to tau of. Therefore, if I take the topology equal to p of x, then this is a topology. Are you sure? And this is okay. This topology is called discrete topology. Okay, so let me write as tau disk. Tau disk is discrete. Okay, this is discrete topology. Now suppose tau is some topology on X. What is the relation between tau and tau disk? Remember, tau is always contained in Px power set, but this is equal to Px. Therefore, any topology is a subset of the discrete topology. You understand that? And the third is the other extreme. Okay, here what we wanted to say. So let us again think about. Okay, see, these are the things I am going to teach you one trade secret, right? Now, what sets are going to be open here in discrete topology? Any subset. If A is a subset of X, this is already open in discrete topology. Right? Why? When A is open, it has to be an element of tau, the topology. But what is the topology? Power set. What is power set? Set of all subsets of X. Therefore, A is open. Do you understand? Therefore, every subset of X is open. In particular, if I take any element X in capital X, let us look at the singleton X. This is a subset. Yeah? And it belongs to P of X. Therefore, every singleton set is open. Do you understand this? Right? Now, what is the advantage? This is where I am going to give a trade secret. Let me just put it as a thing. This is very important. The trade secret is, okay, whenever a topology is given, okay, ask, okay, or look for some natural, minimal, or simpler, okay, given a topology, okay, take arbitrary X in X, then look for some natural, minimal, simpler open set, that is simpler element in tau, that simpler open set U, so that X belong to U. Okay, and I can use any word. This is nothing, there is, okay, I am not defining what is natural, what is minimal, what is simpler. You understand that? As you go ahead by looking at various examples, you will pick up what we want. Okay, I can also say most economical. There are so many ways of saying. Okay, or most convenient, most comfortable, whatever you want to say. Okay, don't worry, we have this word, and I am going to illustrate this principle here. Now suppose XD is a metric space, okay, and tau D is a matrix topology. Okay, now, okay, therefore if you give me any X, what are the natural or minimal or simpler or most economical open sets containing X? They are essentially BXR, as R is positive, or if you want, you can say Bx 1 by n for any natural number n. You understand that? There is nothing like the minimal, there is nothing. Okay, you understand that? There is a lot of things, any one of them is natural for us, right? Are you following? For example, if I have an R2, if I take an origin, okay, right, or take the point 1 1, okay, now take the first open quadrant, that is xy is positive, x is positive, and y is positive. That's the first quadrant. This set U is open, and therefore 1 1 belong to that. That's an open set, right? 1 1 belong to this open set. But what is a very natural open sets for me? Take small open balls around this. That's it. These are the most natural open ball. Do you understand? Don't worry, just have some kind of faith in me. As we go along in each of the examples, I'm going to emphasize this point. And most of the topology, when you learn concepts later, when you want to talk about density, open, closeness, limit point, accumulation point, cluster point, boundary point, all these things will be very easily understood. Even continuity, okay, you'll, okay, the question to ask is, given a point X, look for in some sense a minimal, natural, simpler, most economical open set containing that point. Okay, let us look at the second example, discrete space example. X, and this is tau discrete. Right, now if you give me an X in X, what is the most natural, simplest, minimal open set here? Because I already said it for you, singleton X. X belong to singleton X, right? Singleton is a subset. X is an element. X belong to that. And what do you know about singleton X? This open. Now you give me any open set U which contains X, then X belong to singleton X, and singleton X is contained in U. Do you understand that? Are you following? Therefore, singleton X is the obvious choice. Is the obvious choice now. There is, okay. For that matter, any set U which contains X, that will be an open set. Okay, because it's discrete. Therefore, yeah, any set is open. Therefore, any set I want an open set which contains X is same as saying take any set which contains X. That's an open set. Okay, that's very good. But what is the minimal here? Now I am going to use what is the minimal, most natural. Minimal is singleton X itself. Why? Because X belong to singleton X. This is the open set which is contained in any open set. If U contains X, then this must happen. Do you follow that? Sure? So we will look at few more examples. You will feel very comfortable. Don't worry about it. Okay. Now the third example. Third example is other case. Suppose X is again a non-empty set. Now, if tau is a topology, remember there are two elements which have to be always there. Right? What are they? Empty set and X. Right? So if you have a group G and you want a subgroup, okay, the identity element must always be there. Or if you have vector space, W is vector subspace, then the zero vector should always be there, right? These are the natural things, right? So similarly, if tau is any topology, it has to be there. Therefore, let me check if I take tau to be equal to only empty set and X. You understand that? Remember what is tau? It must be a subset of X. Power set, right? That means it must have certain subsets of X. What are the two subsets of X I am taking? Only empty set and X. Yeah, is this a topology? If it is a topology, and I will call it is indiscrete. Okay, this why this is a topology? The first condition, empty set and X belong to tau, that's correct. And second, take an arbitrary union. What do you have in that union? If you have it, okay, this is a collection of subsets coming from here. Therefore, if X belong to this, then what is union? It is X. Okay, if X does not belong to that, that means every element in this collection is empty set. Therefore, it is empty. So it again belong to tau indiscrete. You follow that? And third, and you have U and V in tau indiscrete, right? So indiscrete. Then what happens? Either U is empty. If one of them is empty, okay, U is empty or V is empty, then what is U intersection V? That's empty. Yeah? You follow that? So what is the left out case? Left out case is U is not empty and V is not empty. But U is not empty and V is not empty, but U and V belong to the topology, indiscrete topology. That means it must be X. Therefore, U intersection V is X. Have you understood? Yeah. So this is case 1. Case 2 is U is not empty, and remember logic, V is not empty. But U, V non-empty and belong to this collection. That means what? U equal to X, V is also equal to X. Therefore, what is U intersection V? X. Yeah. Therefore, this is called this tau. This is called indiscrete topology. Right? Now I asked a question earlier. Do you remember? Let's look at the discrete topology. Let tau be any topology on X. What is the relation between tau and discrete topology? What is the answer? Tau must always be a subset of the topology, namely power set. Now what should be the natural question I should ask here? If tau is any topology on X, then tau indiscrete is contained in tau, because tau will always contain empty set and full set. You understand? Right. And what is another natural question I should ask? Suppose X is any element here, what is the simplest open set containing X? There is only one set, right? Namely, right? Okay, in this case, the simplest open set given an element, the simplest open set is Well, there is only one open set which contains that element, namely X. Have you understood? Okay, right. Now I am going to do, this is the third example I believe. Let's do a fourth example. Okay. Fourth example, let me take X equal to set of natural numbers. Okay. For me, natural number starts with 1, 2, etc. Okay. Because Bourbaki, I believe, starts with 0. That's quite unnatural for me. Yeah. Because we Indians gave 0, right? Only after that 0 was added to India, the number system. Okay. Right. Anyway. So n is natural. Now what do I want to do is very simple. Okay. Let us look at I will define the collection. Okay. First, un to be, okay, set of all k in n such that k is greater than or equal to n. That means this starts from n, n plus 1 and so on. You follow that? Yeah? Right. Now I want to know, if I look at tau to be un as n varies over n, notice that this is a subset of p of n. Okay? I want to know whether this is a topology. Right? Yeah. As I have written, I have to start with 1, that will mean 1, 2, 3 n. Therefore, that means, okay, u1 equal to x. You follow that? Therefore, that belongs to tau. Fine. But empty set, it may not. So what do I have to do? I have to include empty set to this. That is empty set union this collection. Do you understand that? Therefore, if you say u belong to tau, what does it mean? U may be empty set or you must be one of the uns. You follow that? Because none of the uns can be empty. You follow? Therefore, I have to include empty set. Have you understood? So the first condition is satisfied. So what is my tau? Tau is empty set union un as n varies over capital. Alright? Okay. Now what is that I have to do next? Arbitrary collection. Suppose ui belong to tau. Right? I want to know whether union ui, okay, belong to tau. Okay. What is ui? Let us assume I is an I. Right? Right. Okay. Now each of the ui, this belong to tau. If suppose it's empty, I don't have to worry about. Okay. Are you following? Either ua is empty, in which case let's not worry about. Okay. Are you following? Suppose ua is not empty. That means ui, even though I call it ui, oh sorry, this ui should not be confused to un. Okay. So let me just look at a different notation. Let me call it at vi. Vi. If vi is not empty, then vi must be some u of ni, where ni is a natural number. You agree? Accept it? Yeah. So what do I want to prove? Whether union vi, I in I, the indexing set, whether it is again tau. Have you understood this? Just to make sure that you understand, let me look at, suppose v1 starts from un1. That means it is going to be, let us say, um. That starts from m plus 1, etc. And v2 un, which starts from n plus 1, etc. Right? So what is v1 union v2? For example, m equal to 10, let us say, and n equal to 20. What their union? Right? That will be what? uk, where k equal to minimum of m and n. Do you understand this? Yes, right? Okay. So I hope this build your intuition. Now let's look at. Therefore, my Vi, if assume that okay, Vi is empty, okay, the union is not going to contribute. You understand that? Therefore, let's assume none of the Ui's is empty. Then Vi is U of Ni. What do you think union Vi should be? I'm sure your intuition is already built. What should it be? Should be Uk, where K equal to minimum of Ni, I in I. Yeah? Do you follow that? Why? First, why the minimum should exist? Why K exists? The reason for that is look at Ni as I varies over I is a subset of natural numbers. Therefore, I can use so-called well ordering principle. Okay, this is a non-empty subset of natural numbers. Therefore, it has a least element. That least element is the minimum, right? That is what I call as K. Do you understand? So it exists, right? Okay. Are you following? Yeah. Therefore, this K equal to some Nj where J is nice. So for a fixed J. So there exists a J in J, sorry, J in I, that K must be equal to Nj. Because minimum, when you say minimum, what does it mean? It's an element of the set. You understand? Therefore, K must be an element of the set Ni. That means there is at least one J so that my Nj must be equal to K. Yeah? Therefore, if you give me any Ni, okay, what's the relation between Ni and K? K is less than or equal to Ni. And what is the relation between UNI and UK? UNI is contained in UK because remember that UN, if M is less than N, less than or equal to N, then UN is a subset of UM because UM starts from M plus 1 onwards, N is greater than M. Are you following? Yeah, and this is true for all I. Therefore, what do I know? Union UNI is contained in UK, right? Very good. And of course, UK is contained in that because K is one of the Ni's. You understand? Therefore, union UNI I in I equal to UK. That is union VI I in I equal to UK, and hence it's an element of tau. It's in the topology. Have you understood? Yeah. Now, how about intersection? Okay. Suppose I have U, V, and tau, then U is something like UM. That means M plus 1 onwards, and UN that is equal to N plus 1 onwards. What is the intersection? I'm sure all of you know. U intersection V equal to UM, where M is maximum of dependent. But if one of them is empty, suppose U is empty or V is empty, U intersection V is empty, that is taken care. Okay, so I am assuming these are non-empty. Okay, if they are empty, that's all. So what do you think I have proved? So I have proved this is a topology, a collection of UNs. Okay, there is only a countable collection of subsets. Remember, power set of N will be uncountable, right? But the collection tau is a countable collection, including the empty set, right? So this is a topology. Okay. Now, what is the question you would like to ask? All of you should know, right? Suppose I give an integer capital N. Okay. What are the simplest open set? What are the simplest open set? And okay, U which contains N. Go back. So, what are the open sets? The non-empty open sets are the form UN. Therefore I want it to say n belong to this, right? And when does what is un? Un starts from n plus 1 onwards. Therefore my capital N is an element there. So what does it say? My n should be greater than equal to n. That is same as saying my n should be less than equal to capital, right? And therefore what is the simplest thing? Now there is a simplest, namely u capital N. That's the simple. For u1 will be there, u2 will be there, un minus 1 will be there, and u1. Are you following? For example, if my n equal to 3, the simplest open set containing 3 will be 3, 4, etc. Of course, 2, 3, 4 also have, and 1, 2, 3, 4 also has, but this is the simplest open set. Have you understood? Okay. Okay. Right. Yeah. There is an analogous of this. I will just leave this question to you. Please think about. This is the 5th example. There, something very similar, but then it requires little more analysis. Okay. What is that? Now let me take x equal to r now. Okay. Now let me collect for any real number a in R. Let me define ua to be the interval a infinity. The set of x in R, and such that x is greater than, right? So what are these sets? These sets are, yeah. Now let's look at tau. This is collection ua in. I want to know that this is a topology. Okay. Before you watch the next video, please think about, this is similar to the earlier one, but then here we used well ordering principle, etc. to arrive at something. Here we move to do something else. Okay, that's fun. Try. Okay, if you have watched my real analysis lectures, you will find it very trivial question. Okay, try it. Either it's a topology. So assuming it's a topology, I will call it tau ray. This is, see, this is called a ray, right ray. Okay, so I will simply say right ray topology or simply ray topology, because similarly one can define left ray topology. How will you define? Think about left ray topology. How to define? Assuming this topology, we have not checked any of those things, right? Please do that. Okay, come back in the next lecture. We will. Yeah, please check that. In the next lecture, we will do all these things. Okay, take care, stay safe. We'll meet again.